Hi all, in this video we'll understand binary search tree and let's also discuss what binary search tree is, how insertion and search work, and why binary search tree is so powerful in DSA. Basically, a binary search tree is a special type of binary tree that helps us to search data efficiently. Binary tree means each node can have at most two children, but a binary search tree follows few extra rules that makes searching fast. What are those? It follows three simple rules. Rule 1 will be all values in the left subtree are smaller than the node. That is, left subtree, all values in the left subtree will be smaller than the node. And rule 2 will be all values in the right subtree are greater than the node. That is, values in the right subtree will be greater than the node. And rule 3 will be that left and right subtrees are also binary search trees. That is, left and right subtrees are also binary search trees. For instance, if any of these three rules break, it is not considered a binary search tree. So it is a mandate to have all these rules satisfying for a binary search tree to exist. Now let's start to build a binary search tree. Okay. Suppose we have a node, say 50. So this will be the root node of our tree. Every binary search tree starts with a root. Now let's insert, let's say the value as 30. Okay, let's insert 30. So 30 is smaller than 50, so it goes to the left as per the rule. Okay, now let's insert 70. 70 is greater than 50, so it goes to the right. Now let's insert 20. Firstly, 20 is smaller than 50, so we go to the left. Now we check again here. 20 is smaller than 30, so it goes to the left again. Okay. Now let's insert the value of 40. 40 is less than 50, so it goes to the left. And we compare it with the 30. Here 40 is greater than 30, so it goes to the right. Okay. And similarly, 60 will be a left child of 70, and the value of 80 will be the right child of 70 as per the rules. Okay, so this is the final binary search tree. Now let's see how searching works in binary search tree. Let's suppose we want the value of 60 that is to be found in this tree. We got to compare it initially to the root. Okay, so 60 is greater than 50, so we go to the right. Now compare it with 70. 60 is less than 70. As per the rule, we go to the left. Okay, and here we found the value of 60. At each step, we discard half of the tree, just like binary search. Now let's look into the tree traversals in brief. So we have three types of tree traversals. One is Inorder, one is Preorder, and one is Postorder. Okay, so let's take the same tree that we had. 30 we had, and then we had 40 here, 20 here. Then I suppose we have 70 here, 60 here, and 80 here. Okay, now let's look into Inorder traversal first. So Inorder traversal basically follows the rule of left to node to right. So the order would be 20, 30, 40, 50, 60, 70, and 80. So you start from here, you go like this, this way, you hit 60, you hit 70, and you hit 80. It ends like this. So basically this is Inorder traversal. Okay, and if you observe that in binary search tree, Inorder traversal always gives you the values in a sorted order. Now let's come to Preorder traversal. Okay, so this traverses the list in the order of node, left, and right. Okay, so the order would be 50, 30, 20, 40, 70, 60, and 80. So it goes like 50, 30, 20, 40, 70, 60, and 80. So this would be the pre-order traversing. Now coming to post-order. The order would be as left, right, and node. So the post order would be 20, 40, 30, 60, 80, 70, and 50. So you start from 20, you go to 40, and then you hit 30, and then you go to 60, and then you go 80, 70, and up to the root node. Okay. So it is mostly used in, this particular thing is mostly used in deleting a tree. This particular thing is used in mostly serializing a tree or something in those sort of applications. And the in-order traversal is mostly used for getting the sorted order. So now coming to the time complexity, suppose if the tree is balanced for all these operations like say search, insert or delete, the time complexity will be big of log n, because at each step we move either left or right. But binary search tree is not always balanced, right? Let's say we have 10, we have 20, we have 30 and we have 40. So this is the binary search tree, suppose, which is not balanced that we have. Here you see the elements are inserted in a sorted order and the tree kind of becomes skewed. Now binary search tree behaves like a linked list here, and therefore the worst case time complexity of this binary search tree would become big O of n. So this is how binary search tree works. Basically binary search tree gives fast searching, but only if it stays balanced. Thanks for watching.